So let's see. If someone entered the student name as a KULINAL. I'm not sure who he is, but yeah, please make sure that you entered your student number starting with the 뭐야? 이럴 수가. 네, 답이 공개가 됐네요. Okay, so yeah, yeah. Please make sure that you entered your student number. Yeah. So someone must have entered KULINAL twice. Okay. Okay. So in terms of our lecture material or slides, we covered chapter 1 last time, and then we briefly discussed about something called the idempotent, which has the property of p squared is equal to p. So that was the topic of the last quiz problem. And let's quickly cover lecture 2. So you guys know the transpose and this adjoint, and also again I think I mentioned that we only deal with the real values, not a complex numbers, and so you don't actually need to care about this Hermitian. But yeah, in the case of a matrix having all the real values, but if we extend it to a complex values, and then there is something called this Hermitian conjugate, or in short Hermitian, where we denote it as A star, and this guy is not only transposing your matrix, but also it takes the conjugates of all the complex values. Okay. And they have some analogy where in the real world case, if A transpose is used, and then almost all the properties or formulas involving this A transpose, this A transpose should be changed into a Hermitian. Okay. And you guys know the inner product and cosine similarity and some MLM notations and orthogonality. So by using this inner product, we say that two vectors are orthogonal if their inner product is 0, right? And also, although I'm not gonna mention about this complex number case, but in the case of this inner product defined as X transpose Y, I mean this guy in the case of complex number case, and then this X transpose is actually changing X Hermitian. Okay, so in the complex number, the inner product is defined as this. Okay, I mean, but when handling the machine learning problems, we barely use this complex numbers. But I saw some of the machine learning papers that allows to use the complex numbers as our parameters and also activation values in the deep learning cases. But I'm not sure how practical it is, or yeah, how useful it is in practice. But anyways, so that's that. And yeah, we can extend this as the orthogonality between the two vector sets between x and y. And so large X and Y are sets of wave vectors in a same dimensional space, and we pick up any vector from X and any other vector from Y, and then compute the inner product, and if it's always 0, and then those two sets are called orthogonal. Okay, and yeah, this orthogonal matrix. Okay, orthogonal matrix. The definition of it, I mean, I think we discussed about it already, but first of all, this orthogonal matrix, I mean, yeah, we can forget about this unitary, because that is the analogous notion in the complex number cases. But again, we will not care about this complex number cases. So we can only take care about this orthogonal matrix. And first of all, this orthogonal matrix is square matrix, and each column in our square matrix is orthogonal to the other column in our matrix. Okay, so we pick up any pair of column vectors in our matrix if they are orthogonal all the time, and then it is this square matrix is called orthogonal matrix. Okay, and yeah, it has an interesting properties of this guy. It's like Q transpose Q equals identity in the case of real world case. I mean real number case, right? And Q is again square matrix, and thus it gives us the inverse matrix of Q. So here we can see that the Q inverse is actually Q transpose. Okay, and also when studying this inverse matrix, we also studied that in the case of a square matrix, if we found a matrix that satisfies this, I mean, we are talking about this Q transpose. We found this matrix when multiplied on the left, it is producing a identity matrix, and then it is actually the inverse matrix of the original matrix Q, and also automatically, even if we switch the order of this multiplication as this Q transpose, I mean that will also still produce identity matrix. Okay, and then if we call this matrix as for example like S, and then what is this? This is S transpose, right? And so it will produce the identity matrix, right? And so this S is still an orthogonal matrix, which has the orthonormal columns, right? Which are, I mean, where every pair of columns are orthogonal to each other, and also, I forgot to mention about additional condition that each column length should be 1, right? And then, I think we proved this guy in the previous class, right? So if we have like 3 by 3 matrix, and suppose we have 3 columns, and if they are orthonormal, which means that every pair will produce 0 inner product, and then their length is 1 for each of these 3 column vectors. And then if we compute the multiplication with the Q transpose on the left, so this will be our Q transpose, and then the resulting matrix will still be 3 by 3, and then let's apply the inner product perspective of this matrix multiplication, which means this guy times this will produce this guy, right? And then it will be the inner product between the same vector itself, right? And so the same vector, I mean inner product between the same vector will produce the vector length squared, right? And then again, I said that each column vector should have the length of 1 to be an orthogonal matrix, right? And so this will be 1. And similarly, we can easily see that the diagonal elements are all 1s, right? But what about the off-diagonal part? For example, like this part, it will be the inner product between this and this, right? So it is basically the inner product between the two different vectors that we have as our column vectors. So all these values should be 0, right? So that is a kind of easy proof of this orthogonal matrix is satisfying this equation. And thus we can easily prove that Q transpose, this guy, is inverse of this original matrix Q. Okay, and then now based on the property of this inverse matrix, which is that if this guy, if we found the one matrix that satisfies that, and then this guy, which is a switched, I mean, the multiplication of the reversed order should also be identity, right? So that is even though we proved it, I mean, even though we didn't prove it, we just take it granted. Okay, in the case of square matrix, right? Okay, and so we can agree that this guy is also satisfied. And then what does that mean? When Q transpose our original input matrix, saying maybe S, and then Q transpose and the Q, it will be S transpose, and so it will be identity matrix. And what does that mean? I mean, in order to satisfy this, suppose we have an S as a 3 different columns, and then S transpose should, I mean, multiplication with it, with the S transpose on the left, should produce identity matrix, and thus it also means that this S is also an orthogonal matrix, which means every column has the length of 1, and then they are orthogonal to each other, right? So from this property, we can conclude that S has also orthonormal columns, right? And what is S? S is Q transpose, right? What is Q transpose? Q was orthogonal matrix, and our conclusion, or my point, is that even if we just transpose this orthogonal matrix, and then now in this transpose matrix, let's just consider their columns, right? And then these columns are also orthonormal. Okay, so originally we started from the matrix that has the orthonormal columns, but our rows are also orthonormal, right? In case of this orthogonal matrix. Okay, so that is another very interesting property. Okay, so more intuitively, for example, you guys know the Gram-Schmidt process. So let's just quickly build up kind of a matrix Q. For example, let's see if I can do well. Let's see. Suppose this is our first column. Okay, so this is certainly having the length of 1, and then having a certain length, and then what should be the okay. Let's just actually do the Gram-Schmidt process. Sorry. So suppose this is first column, and then suppose our second column was originally 1, 1, 0, 0, for example. And then how do we perform the Gram-Schmidt process? and then we project this guy onto the line spanned by this, right? And then that is, so we have this line. So suppose this column is U, and we have the line spanned by our U, and suppose this guy is the vector A, and then we have some vector A, and then we want to decompose this A into two parts where the first component is parallel, or is on the line spanned by U, right? And then we have this second component, right? So in general, this this vector plus or added with that blue vector should produce the original input vector A, right? And so we have to first compute this green part, right? How do we compute this green part? So if U has the length of 1, okay, then so we can apply the cosine kind of thing. So if it will be basically A times cosine theta, right? So I'm just quickly deriving the Gram-Schmitt's process. Okay, then in this case we know this cosine theta is A inner product dot U divided by A and U, right? So that is the inner product formula. And then if we assume that if we are given U as a unit vector having the unit length, and then this part will be gone because they will be 1, right? Okay, and then we can just first compute the inner product with this guy, right? And then what is the inner product with between A and U? Yeah, it is just inner product between these three elements. Okay, then this guy, right? Inner product has 1 over square root 3. Okay, and then what about this guy? The length of an A, or the norm of an A. What is that? What is the value of it? 1, right? Because A is 1, 0, 0, and then 1 squared, 0 squared, 0 squared, and square root of it, and then it will be 1. Okay, so it will be 1. Okay, so this part, okay, this part is now A times 1 over square root 3, right? Because this whole part is 1 over square root 3, right? So far so good, right? Any questions so far? Okay, so we computed this part, which is a projected portion, right? And then we have to subtract this guy from A, right? So if we subtract, if we subtract this green part, so far what we did was to compute this green part, and then if we subtract this part from A, and then we will obtain this blue part, which is the orthogonal part from the previous vectors, right? Okay, and then that is 1, 0, 0 minus, so which part is wrong? Where did I do wrong here? Okay. So again, yeah, this guy is, I mean, yeah, cosine theta is a scalar and A is a vector, right? So yeah, this basically doesn't make sense. So if we wanted to compute the length of this line segment, right? And then we should have started from A norm, right? Not A, right? Okay, so that part. And let's see. And then even though the length of an A is 1 in this particular case, but yeah, we don't actually need to compute this the length of an A, right? Because they will always be cancelled out. And then the resulting formula will be A dot U, which is an inner product divided by the length of U. But if we assume that the length of U is always 1, because we can always normalize during each step of our Gram-Schmitt's process. And thus, we can always remove this part, okay, ignore this part because it will be always set as 1. Okay, and then overall, the inner product itself will specify the length of this green line segment, okay, and this is our inner product between A and U, right? And that will be our length. But for this vector, so far we only computed the length of this vector, right? So we have to multiply it with the direction, right? So what is the direction pointing to that? That is just an U, right? So this part should have been U, right? So where is U? U is this guy, right? Okay, and then what is so square root 3 and square root 3, 1, 1, right? And so it will be, so we can simply write it in this form, right? So this one, 1, 1, 1 times 1/3. I mean that is the line, the vector of this green part. And then if we subtract it from the original vector, and then we will obtain this blue part. What is the blue part? Then this A is 1, 0, 0, and minus this vector, and so the vector is Is it correct? Okay. Okay. So this guy, although it's sorry for the a little bit messy kind of back and forth kind of thing. But this blue, we computed this blue part, which corresponds to that vector, right? And then we have to further normalize it. I mean, so that the length of it becomes 1, right? Okay, and so it will be something like in terms of a direction, it will be 2, 1, 2 minus 1 and minus 1 times some alpha, which makes the vector length as 1. 4, 1, 1, square root 6. Right. Although it's a little bit we don't actually use this scalar multiple within to specify the particular column within a matrix, but you guys get the point. And so here, looking at the ratio, it's a 2, -1, and -1, right? And then in terms of a ratio, it will be 1, 2, 1, 2, 1, right? And so 1, 1, 1, and 2, -1, and -1, and then if we just compute the inner product, and then we can easily verify that they have a 0 zero inner product, which means they are orthogonal to each other, right? Okay, and then suppose the third vector. So A was 1, 0, 0, and then from that we obtain this vector, and then now suppose the third vector is maybe 1, 1, 0, for example. Okay, so in this case, what will be the next step of the gradient descent? So we first project this guy with this guy and this guy. I mean, computing the inner product, right? Which means now our subspace spanned by the previous two vectors, not the single vector. I mean, because it is spanned by the two vectors, it is actually the plane that we have to project our third point into, right? So yeah, it is nothing but just a two-dimensional subspace compared to the one-dimensional subspace. And so in order to compute the projection to this plane spanned by these two, then we just compute the inner product with this guy, with this, and this. And then do the similar calculation, right? And then subtract that projected part to obtain this orthogonal part like this blue part, and then we normalize, and that will be the great Gram-Schmidt process, right? So although I mean, yeah, usually this Gram-Schmidt process, because it is involving this normalization of the vector lengths, I mean the computation itself may become a little bit messy, but yeah, the overall process should be clear. Okay. So any questions so far? Yeah, 네. 하는 이유요? 하는 이유? 저걸 해두면 좀 여러 가지로 좋아요. 왜 좋냐면 okay, so why is it, I mean, where is it useful? I mean, to compute the orthonormal version of our columns compared to the non-orthonormal versions of the columns. So for example, it is related to least squares problem, but let's think of the projection spanned by these two non-orthonormal vectors. So for example, you have a single point over here, and then what is the orthogonal projection of this point onto the subspace spanned by these two vectors, which are not orthogonal to each other. Okay, so they have some angle, not different from 90 degree. Okay, so in this case, so this projection. Okay, so that projection. How can we suppose the matrix A is this two column of A1, A2, and A1, A2. Okay, and then let's consider this vector x. Yeah, so suppose A is A1 and A2 are three-dimensional vectors, and also x is three-dimensional vector, and projection onto columns of an A. Yeah, columns of an A means the subspace spanned by the columns of in A, right? Okay, so does anyone know the formula of it? AX. AX. So yeah.
Inverse of A transpose A, and then times A.
Yeah. Times A transpose. Right.
Oh.
So it is coming from the normal equation of A transpose AX equals A transpose Y, where Y is our projected vector. No. Yep. Okay. So let me. Okay, so let me make it step by step. Okay, so this projected point, yeah, let's call it as y. Yeah, let me just change it as a, vector a, because I want to use x in a different position or different place. Okay, so this y vector, which is an orthogonal projection of an a, okay, and then this y will be anyways a linear combination of a1 and a2. I mean, yeah, even before it is an orthogonal projection, but the first assumption or kind of a necessary condition to become y is that y should be inside of the span of these two vectors, a1 and a2, right? Which means y is always represented as a linear combination of a1 and a2, right? So let's think of this projection. I mean, non-orthogonal projection, although it is barely used, but suppose the projection point is over here, and things like that, right? But still, yeah, what is the meaning of the projection? Whether it's orthogonal or not. Their angle might be different, like maybe 60 degree and 110 degree, but all the 3 points should be on this plane, which means, yeah, those 3 points should be inside of the plane spanned by these two vectors a1 and a2, right? Okay, and so it can be represented. Yeah, so let's see. So let's call it as maybe u. Yeah, sorry for the confusion, but yeah, I want to represent it as a times x, which is a arbitrary linear combination of an a1 and a2, because our matrix A has 2 columns, right? And then the vector x should be 2-dimensional vector, x1 and x2, and then yeah, they are multiplied with each column vector, and then produce this a1 x2 times a2, right? So this will be our projection, right? Okay, and then now, yeah, obtaining y or computing this y is equivalent to obtaining x. And in other words, what will be the particular linear combination coefficient, okay, when where this ax, which corresponds to this point y, and then if we draw this triangle like this, okay, and then when does this angle become 90 degree, right? Okay, so if we use this point, I mean that point will have its own, I mean different linear combination coefficient, but if we just draw this triangle, and then this angle, okay, this angle will not be 90 degree, right? So that will, yeah, give a further further requirement to become orthogonal projection, right? So let's just write that notation, okay? So ay, which is our projected point, okay, this ay, and then let's see. Okay, this guy, okay. So we have to we have to build up the equation that this perpendicular line is orthogonal to this line, this horizontal green line, okay. And then what is this bright green line? It will be u minus A times X. Does it make sense? So again, the projected point is Y, which is the linear combination of the columns of an A, and thus Y should be always represented as A times X. Right? So far so good, right? And so U minus Y, which is U minus AX, is this vertical part. Okay, that vertical part should be orthogonal to this line, this horizontal line, right? Okay, so this orthogonal projection is actually has much stronger condition, which is that, I mean, this guy should of course be orthogonal to this line, this horizontal line. But what if we just make it slanted? For this triangle. So let's imagine this. So we have this triangle, which is kind of vertical to this this horizontal plane, and then let's just make it a little bit slanted, and then this angle may still become orthogonal or 90 degrees, right? So if we imagine it, then if we just make it a little bit slanted, then we can still maintain the 90 degree angle between this line and that, right? And then can it be called the orthogonal projection? It is not, because I mean, what is the kind of true meaning of the orthogonal projection? That means this vertical line, or this bright green line, should be orthogonal to any directional vector or any vector inside of this plane. So that means this guy should be orthogonal to, like, okay, so this is a random kind of arbitrary kind of directional vector inside of this plane. So it should be orthogonal, and it should be orthogonal, and it should be orthogonal, right? Okay, so it should be orthogonal to any vector, yeah, included in this plane. And then how can we represent it as our equations? What will be the equivalent condition? I mean, there will be infinitely many directions, right? Infinitely many different directions. But here we know that this plane is spanned by A1 and A2, which is two finite number of vectors, right? I mean, finite number of vectors, right? And thus, any directions will be anyways a linear combination of these two basis vectors, open A1 and A2, right? And thus, in order to make this bright green line orthogonal to any directions inside of this plane, and then, I mean, any direction, yeah, can be infinitely many different directions, but we only need to satisfy the finite, a finite condition, a finite number of conditions, which means this bright green line is orthogonal to A1 and A2. That's it, okay? Because all the pink lines will be anyways represented as a linear combination of A1 and A2, right? And so if we can guarantee that this bright green line is orthogonal to A1 and also A2, and then any possible combinations, any possible linear combinations of an A1 and A2 will be always orthogonal to this bright green line. Okay? So that's the kind of overall story of this linear, least squares. So this AY should be orthogonal to A1. Okay, that will be the first condition, right? And so let's just write that condition in this form, right? But let's just change it into a transpose, A1 transpose, right? And then also it should satisfy this guy. Oops, sorry. Not this guy. It should be bright green line, which is this guy, U minus ax, right? So u minus ax and u minus ax, right? Okay, and then yeah, at on a high level, let's look at these two equations. So A1 transpose, and we have A2 transpose, and U minus AX, even though we don't know X yet, but X will be some particular kind of particular vector that satisfies this orthogonality. So that will be just a common column vector like this, right? And so we have these two equations, right? And then this one can be represented as this form. So we have a single vector over here, and it seems quite colorful, but yeah. Okay, so it will be 0 and 0. So this is one single matrix equation formula, or matrix equation that we have to satisfy. I mean, we are just going over the normal equation and its derivation. So far, does it make sense? Any questions so far? 네.
U가 평면 위에 있는 이미의
아, U요. U는 평면 위에 있지 않은 이제 임의, 3차 같은 스페이스에 있는 임의의 점. 그리고 우리가 이제 orthogonal projection을 지금 구하려고 하는 거예요. So you can be any point, which is not necessarily on the plane, right? Okay, so so what was A actually? A is, I mean, by using the colorful representation, A is composed of these two columns, right? So this will be our A, right? Okay, so this guy is A transpose because this matrix has rows as the columns of an A, right? Okay, so let's rewrite it. A transpose, and what is this cyan colored vector? It is U minus AX, right? Equal to 0, and A transpose U minus A transpose AX equals 0, and thus A transpose AX equals A transpose U. Okay. So here, let's just remind ourselves. I mean, what are our variable and what are the given vector? So again, x is a variable that we have to solve or obtain, and what's the meaning of that? So that is the linear combination coefficient over here for our projected point y, right? So projected point is represented as a times y. To explicitly represent that, projected point should be on the subspace spanned by A1 and A2, right? So that is the story. And U is our given or input vector. So U is a constant vector. Okay, so we have to compute A, right? So I mean X. So X is A transpose A inverse A transpose U, right? I mean, assuming that A transpose A is invertible, right? But what if A transpose A is not invertible? I mean, yeah. So in that case, we cannot represent X in this form because this matrix is not invertible. But in practice, you don't actually, you don't need to worry about it. So in practice, this one will almost be invertible. Okay. And also, also there is a simple trick that makes this matrix invertible. So what will be that trick? What will be that trick? So that trick is think you guys may have heard about this, but Ridge regression. So Ridge regression. Have you guys heard about it? Okay, in that, yeah, so yeah, it is basically a regression problem. But yeah, but anyways, one simple trick is that instead of using A transpose A, we actually use A transpose A plus gamma times identity matrix. Okay. So in that case, yeah, I mean, for some particular lambda value, it will become non-invertible from invertible matrix. So, yeah, so that is also related to kind of eigen decomposition. But yeah, but in general, if we just add the gamma I, and then it will likely make your matrix invertible. Okay. So in that case, in the place of an A transpose A, we will use A transpose A plus gamma I inverse, because that will be likely invertible. Okay. So in this case, it is called the Ridge regression. And how is it related to the regression? Okay. So it is called the least squares, but how is it? Yeah, how is it related to our regression problem? So for example, yeah, so let's just fit the line of like y equals ax plus b. So it's a completely different problem, but yeah, we just talk about the curve fitting given our data. So for example, suppose we are given 1, 3, and 2, 4, and 3, 7. Okay, and then pictorially, it will be 1, 3, 2, 4, and 7, 3, 7. So in this case, the fitting line will be something like this. So it will, still have some errors, but we want to find this optimal line. Yeah, or equivalently, we want to find the optimal slope and y-intercept, which correspond to this A and B, right? So in this case, how do we formulate it? So we are given this 3, 4, 7, right? And what is our estimation through this ax plus b? Okay, then it is represented as a times 1, 2, 3 plus b times what? 1, 1, 1. Okay. So does it make sense, right? Any questions so far? So we originally, these are the given y values as a vector form, and what will be the our estimation? It will be a times x plus b, a times x plus b, a times x plus b, right? So there will be corresponding three-dimensional vector from our linear equation or linear representation, and thus we want to and then we have to further apply the trick on this part. So this 3, 4, 7 minus, it will be represented, it can be represented as 1, 2, 3 and 1, 1, 1 times what? A and B, right? So we can factorize, we can factor this out into this form, because it is a linear combination of these two vectors and the linear combination coefficient of an A and B. And thus we apply the column combination perspective of a matrix multiplication. And so we bring these two columns to form our matrix on the left, right? And then on the right, we just form the vector composed of this linear combination coefficient. And thus, this is our B, and this is A times X, right? And so, we want to minimize the difference between this vector and this vector. And yeah, we usually formulate it into this form, right? So we want to minimize this guy, right? Okay, then how is this related to that problem where we considered this orthogonal projection? So here, yeah, I mean, by making some analogy, so this is our B, which is a three-dimensional case from this linear regression case, okay? And then this guy is some point, which is always represented as a linear combination of the two columns that we are given in our matrix A, right? And then we want to minimize the difference between this guy and this guy. And then still, this is a vector, and this is a three-dimensional vector. And so once we just subtract this from here, we will still have a three-dimensional vector, right? And so what does it mean by minimizing the three-dimensional vector? So we have three numbers, right? So we have three numbers. So yeah, we consider it's a squared error, right? Squared error. So once we compute this difference, and then we just take the square of each difference and then sum them up. So that is the meaning of this L2 norm squared of this difference vector. Does it make sense? So if you want, I can give you the example. So if you guys understood, and then we can move on. You want to give an example or not? Okay, so okay, then let's move on. And then, so in this case, what is the meaning of this? I mean, geometrically. So we have a particular vector of 3, 4, 7, and then this one is some point as a linear combination of the columns of an A, and then we want to minimize the lengths between these two vectors. I mean, the lengths of this vector, and that means, yeah. So we are given the point U, which is an outside of this plane, and then we want to find some points on this plane, right? We want to find some point on this plane, and then that is always represented as a linear combination of the columns of an A, and thus A times X, which is our Y. But we want to minimize the vector lengths formed by the difference between that one and that one. Okay. In that case, which vector length is shorter between like this guy or this guy or this guy? The shortest length vector will be this guy, right? And in order to create the shortest vector length, yeah, we have to perform orthogonal projection. So that's the relation, or that's the connections between this linear regression to make the error. I mean, to minimize the error. Okay, so that is related to this orthogonal projection geometrically. Okay, in this form. Okay, and then yeah, back to this ridge regression. So in this case, the solution for this is obtained as this normal equation, because this orthogonal projection problem is exactly the same as least squares problem to minimize this distance between the given y's and our linear combinations of the input values. Okay. And then in this case, again, A transpose A is invariable, and then it will be fine. But if it is not, and then we can use this A transpose A plus gamma I to make this matrix invariable. Okay. And also, even though we will not cover this, but this has also really nice interpretation from the perspective of the probability theory. So in this case, it is equivalent to just imposing the Gaussian distribution prior on our parameter x. Okay. So in the context of a Bayesian kind of statistics, like combining prior and the likelihood to compute the posterior. Okay. But yeah, so we will skip that part. But yeah, if you want, yeah, it will be really great to study their relations as well. If you are also like heavily using the probability and things like that in your own research. Okay, and then now let's get back to the student's original question. Okay, so the reason why I wanted to describe or discuss about this orthogonal projection is because, okay, so in this case, what is the orthogonal projection? So let's get back to this problem, so this is our U. So what is this formula? Projection of U onto the column space of an A. So yeah, so this is Y, right? So this is Y, right? Because Y was defined as an orthogonal projection, but Y is represented as A times X, right? And what is vector X that satisfies the orthogonal projection, not other non-orthogonal projection. In order to satisfy that orthogonality or orthogonal projection, X should satisfy this solution, right? So we can plug this guy into the upper equation, like A times X, where X is this guy, which is A transpose A inverse A transpose U. Okay. So this whole representation, okay, shows the formula for orthogonal projection, okay, onto the column space of an A, given a matrix A. Okay. So at a high level, let's just call this matrix as maybe P, and then it can simply be represented as P times U, right? So yeah, this orthogonal projection onto the column space of an A is represented as some matrix times a given vector, right? So what's the point that we can make here? So yeah, one kind of an interesting kind of discussion by observing this representation is that, so we mentioned or we discussed about the relationship between the linearity or linear algebra and this matrix stuff, right? So what was the connection between these matrices and linearity? So if you guys remember, if we consider the transformation, not necessarily a linear transformation, we just consider the mapping or function or transformation that takes the input as a particular dimensional vector and mapping it into another dimensional vector. For example, like we can imagine some function that sends like a five-dimensional vector into three-dimensional vector. Okay, and then this mapping can be defined, right? But if this mapping is a linear, which means, so what is the definition of linear transformation? Let's just review that first. What's the definition of the linear transformation? So I used this page a lot, so let me make a new page. So what's the definition of the linear transformation? So we have a function f, and let's suppose we have these two kind of closed or two particular function mapping between x1 and y1, and another mapping between x2 and y2. So in this case, if f is linear, and then for any x1 and x2, this linear combination first, and then giving it as an input to our function, that should be the same as this guy, right? So which means, yeah, whether we take the linear combination first in terms of an input level, and then compute the function output, that is always the same as we first compute the function output, then combines them linear. I mean, do the linear combination by using the same linear combination coefficient. Okay. So in terms of a sending the 5-dimensional vector to 3-dimensional vectors, and then we can just first linearly combine this 5-dimensional vector first, and then send it to a 3-dimensional vector using our function. And that resulting vector, okay, that resulting vector is the same as we first send the two 5-dimensional vectors into their own 3-dimensional vectors, and then do the linear combination, and then the result will be the same. Okay, so that property is the linearity in our transformation, right? So in our vector space, I mean, if our input and outputs are all vectors, okay. Again, if our input and output are all vectors in a particular dimensional space, and that that transformation is linear, and then our linear transformation of a vectors will always be represented as this matrix times a vector multiplication, right? So we proved it, right? No? Does anyone remember how we proved it? Yeah, it's really simple. So let me just yeah. So no one seemed, yeah, probably, yeah, almost no one, yeah, seem to remember. But I may, yeah, or I may have not taught, but yeah. So this guy is y1, right? So we have y1 over here, and b times y2, right? Okay, and then okay, so yeah, this linearity, okay, this linearity should be satisfied for any, yeah, any choice of x1 and x2, right? So this linearity should be always true, regardless of any choice of x1 and x2, right? So let's imagine x1 as 1, 0, 0, 0, because we are talking about the 5-dimensional vector, not 5-dimensional vector. Okay, so let's just consider like R2 sending it into R3. So our function is sending R2 or the 2-dimensional vector into 3-dimensional vector, and then suppose our function output is and like this, okay, and then given some arbitrary vector x comma y. So this guy is always represented as x times 1, 0 and y times 0, 1, right? Okay, and then this, yeah, x comma y is linear linear combination of 1, 0 and 0, 1, right? And thus yeah, it is f of x x 1 0 and y times 0 1, right? So if it is a linear transformation, x times f of 1 0 plus y times f of 0 1, right? And so x times 3 4 5 and y times 1 0 2, and that will be 3 4 5 1 0 2 and xy. Yeah, sorry for bad handwriting, but yeah. So in this manner, so we only used the linearity, like that kind of a superposition relationship. So that is composed. Yeah, that is called the superposition equation or relationship. So we just applied it for these two particular examples to represent this arbitrary input vector as a linear combination of two particular input vectors 1 0 0 1, right? And then suppose we have this two outputs, and if this function f is a linear, and then through this derivation, it can be represented as a linear combination of the output vectors, right? We can also do the linear combination on the output level, and then this output vector linear combination of these two output vectors can be vectorized into this form, right? Because it's also still a linear combination of these columns, which can be represented as a matrix multiplied on the left of a particular vector x. Okay, so in our conclusion here is that we started from the linear assumption, but that linear assumption always leads to this matrix vector multiplication. So if vector to vector transformation is linear, then that transformation is always represented as a particular matrix times a input vector. So that's the connection between the linearity and kind of matrix stuff in the context of a kind of a vector to vector transformation. Any questions about it?
Just Gauss-Schmidt process, does it give a orthogonal projection on the original space?
I didn't hear the first part.
The Gauss-Schmidt process, does it give an orthogonal projection on the original space during the process?
We haven't answered the original question. I mean, that is directly related to the student's question, right? So let me finish that up quickly. So far so good, right? And so the point here that I wanted to make is that so this is anyways represented as a linear combination. I mean the matrix times the input vector, right? And thus here our conclusion is that this projection is kind of intuitive kind of process, right? Not necessarily a linear or not, right? But from this representation, we can conclude that this orthogonal projection is actually a linear transformation, which means when doing this orthogonal projection, we imagine like two different input vector, and then first to do the orthogonal projection of each point separately. Okay, and then from those input points, we just linearly combine them to produce another vector, and then consider it's a orthogonal projection. Okay, that orthogonal projection is the linear combination of these orthogonal projection outputs computed separately from these two inputs. So, linearly combining the vectors like outside of this plane, okay, that will produce the same vector. I mean, that will be equivalent to linearly combining the projected version of the vectors inside of this plane. Okay? So that's the meaning. Right?
벡터가 속해 있는 디멘션을 가진 스페이스의 베이스 벡터, 예를 들어서 인류가 3차원이면 1영역이고 0영역 이렇게 쪼개서 각각을 프로젝션해서
그렇죠.
더하거나
그렇죠.
똑같다.
그렇죠. 그렇게 해석할 수 있죠. Okay, so let me quickly answer the original question of the student. So in this case, so we assume, did we assume any orthogonality of the columns of an A? We didn't, right? So A can have just an arbitrary column, which is not necessarily orthogonal to each other, right? So in that case, the projection formula will be like that. But what if A, or our matrix A, has already an orthogonal orthogonal vectors, which means, so here I drew this example by having some angle which is not a 90 degree, right? So in that case, the projection kind of formula will be really kind of dirty like that, right? And so in this case, let's just think of some special case where we have the two columns are orthogonal already, or orthonormal, right? And then let's just first think of this. So think of these two non-orthogonal case, and then consider the projection point, or orthogonal projection. And now let's think of their Gram-Schmidt kind of processed output, which is a kind of orthogonal version. So the that orthogonal version will be, the first vector will be something like this guy, right? Which is a unit vector of the first one, and then the second one projected, and then we just compute this second version of the vector, which is orthogonal to the first one, right? So these two will be the result of the orthogonal projection of this A1 and A2, right? And then in this case, how about the subspace spanned by the original two vectors of an A1 and A2, and another subspace spanned by these two orthonormal versions of these two? So the subspace will be the same, or the plane will be the same, right? The subspace spanned by these A1 and A2, and the subspace spanned by these two bright green vectors, those two will be exactly the same. So orthogonal projection will not change, right? Because our plane is still the same, and thus orthogonal projection point will still be the same, right? So suppose we we did a Gram-Schmidt process starting from given the input matrix A, and then made the matrix Q, which now has a orthonormal columns. Okay, so in this case, plugging this A into this formula of the projection, or plugging this Q in the place of the A in this orthogonal projection formula, they should be the same. I mean, right? Once we obtained Q from A through orthogonal projection, and then we can guarantee that the projection point will be the same, right? But here the computation will be much simpler when using Q, because this part, Q transpose Q is what? It is identity matrix, right? And thus we don't actually need to compute that the inverse matrix. Okay, so our projection matrix, projection formula, when using this orthogonal matrix, in that case it can be represented as Q times Q transpose U, right? Right? So this is a kind of simplified formula, and thus when doing the orthogonal projection, and then once we obtained the orthogonal versions of the basis vectors from the A. So again, we compare the two situations where A, which doesn't necessarily have the orthogonal columns, but we processed it through the Gram-Schmidt process to Q, right? So we compare between these two cases, and their kind of orthogonal projection will not change at all, right? And also, furthermore, this kind of linear transformation can also be simplified, because this A transpose A inverse, this part will be gone, right? And so A transpose U can be simply, easily computed. Okay, so let's take the break until around noon, and then let's resume after that.
이번 금요일 2시 도전
네.
제가 바로 수업이 있거든요. 혹시 그게 수능에서 바로 전수 수업이다 보니까
네.
내용이라든지 여러 공지 사항이나 이런 걸
네, 내가 그거를 저기 강의 비디오를 내가 좀 거기 바로 올려줄게요. 그래서 그거
다
네.
그날은 그러면 퀴즈라든지 출석이라든지 그런 거를
아, 네네. 네. 네. 네? 이거 퀴즈 본 거예요.
얘가 이런 컬럼 스페이스에
이게 좀 노테이션이 많이 헷갈리는데
네.
그러니까 U가 이제 임의의 벡터고 그러니까 플레인 위에 있지 않은 임의의 벡터가 U고
네.
걔 프로젝션이 지금 X 그러니까
AX, Y.
AX인 거죠.
네.
또는 Y.
네.
아,
네.
그렇군요.
하세요.
그러면
네.
근데 이제
네.
A 매트릭스가
네.
그 A1하고 A2로 구성이 되어 있는 매트릭스인 건가요?
네. 맞아요.
그럼 걔네들의 그냥 리니어 콤비네이션이
네. 여기에 네.
이제
네.
그 개수들이 X인 거예요.
네. 맞아요.
이런 식의 베이스 벡터.
근데 그러니까 제가 좀 헷갈리는 부분이
네.
그 그램슈미트 프로세스라는 게 그냥 일반적인 베이시스를 가져다가 올소 노멀한 베이시스 만드는 과정인 거잖아요.
네.
근데 사실 막 저희가 처음부터 그냥 A1을 노멀로 만들고 A2를 A1하고 이제 올소고널하게 만든 다음에 노멀로 만들고 이런 과정을 반복을 하면 그러니까 이게 지금 이거는 A1하고 A2가 올소고널 하지 않을 경우에 일반적인 케이스를 설명을 하신 거잖아요.
네.
근데 이걸 다 올소고널하게 만들 수 있는데 굳이 이 프로세스를 그러니까 실제로 그
네.
프로세스를 할 때는 이렇게 하지 않잖아요.
아, 네. 네네. 그러니까 이제 여기에 있는 U가 이제 뭐 예를 들면 그램-슈미트 프로세스를 우리가 하는 중에 세 번째로 나타난 벡터다라고 하면은 A1과 A2를 이미 올소 노멀하게 만들어 놨기 때문에 그렇기 때문에 걔에 대한 올소고널 프로젝션을 구하는 게 훨씬 쉬워지고
네.
네, 그렇게 하는 건데 이제 지금 여기서의 상황은 기본적으로 우리가 하고자 하는 메인 잡은 그램-슈미트 프로세스가 아니고요. 네, 아니고 우리가 뭐 예를 들면 한 100개의 베이시스 벡터가 있고 100디멘전에서 아니 뭐 훨씬 큰 디멘전에서 100개의 베이시스 벡터가 있고 그거에 스팬되는 그 서브스페이스로 프로젝션을 우리가 하는 거죠. 네, 그런 상황을 하면 이제 뭔가 우리가 101번째 벡터를 그 그램-슈미트 프로세스를 통해서 구할 수도 있지만 올소고널 프로젝션을 이 100개를 다 하나씩 해서 할 수도 있지만 이제 뭔가 뭐 바로 처리를 한다면
한 번에
네네 그러면
방법이
그렇죠. 그게 뭐 대충 뭐 네, 이런 식의 이제 노멀 이퀘이션이라는 거고요. 네. 실제로 우리가 그리고 그램-슈미트 프로세스가 이제 올소고널라이제이션을 하는데 유일한 방법이 아니라 그리고 또 뒤쪽에도 뭐 좀 그런 얘기가 나오는데 이제 뭐 무슨 모디파이드 그램-슈미트니 뭐 이런 것들이 좀 있어요. 그래서 이게 뭐냐면 이제 좀 기본적으로 에러가 좀 누적된다라는 거거든요. 네, 그래서 이제 에러가 누적된다는 게 이제 첫 번째 올소고널 프로젝션을 방향을 예를 들면 1도 정도 잘못 틀어서 구해놨어요. 그리고 그런 에러들이 실제로 우리가 이제 숫자를 이제 컴퓨터에서 이걸 파이나이트 넘버로 이제 뭐 플로팅 포인트 뭐 이렇게 넘버로 나타낼 때 실제로 에러가 발생이 돼요. 그러면 이제 그 에러가 실제로 이제 뭐 그게 항상 그 에러는 이제 0에 가까운 숫자로 뭔가를 나눌 때 발생이 되는데 이제 우리가 어떤 포인트가 있는데 그 포인트가 이 평면 위에 완전히 이렇게 붕 떠 있는 게 아니라 살짝만 떠 있으면 그걸 이제 올소원 프로젝션을 구해서 그거를 빼면 요 남은 벡터가 굉장히 작아지거든요. 그러면 그 남은 작은 벡터가 우리는 어찌됐건 얘를 길이를 1로 만들어준다는 되는 거는 길이가 만약 0.001이었으면 그거를 뭐 1000배를 해줘야지 이게 길이가 1이 되니까 빵 이렇게 튀게 되고 그렇게 되면 거기서 방향이 여기서는 아주 작으니까 그게 방향이 약간 뭐 한 1도 틀어졌어도 괜찮았는데 빵 이렇게 키워지면서 이제 1000배가 되면 이게 방향이 이제 뭔가 벡터가 완전히 좀 다른 곳으로 가는 그런 식의 에러들이 생기거든요. 그래서 이제 그램시미치라는 게 이게 기본적으로는 이제 그러니까 시퀀셜하게 이제 그리디하게 첫 번째 거 먼저 하고 두 번째 거 다음, 세 번째 거 이런 식으로 하는 거기 때문에 초반에 발생한 에러들이 뒤쪽으로 가면 갈수록 좀 누적이 되는 혹은 그게 에러가 프로퍼게이트 되는 현상들이 좀 있어요. 그래서 이제 그런 것들을 조금 방지하고자 하는 게 좀 그런 게 있고 그 다음엔 아예 이제 이 그램시미치를 하나씩 이런 시퀀셜하게 하는 게 아니라 이 매트릭스를 그냥 통으로 두고 이거 자체를 그냥 좀 다른 방식으로 그냥 올소원을 매트릭스로 변화를 시킬 수 있는 방법들도 있거든요. 그래서 이제 뭐 그런 것들도 좀 배워보려고 하죠. 네.
그러니까 약간 이론적인 부분보다는 실제로 구현할 때 컴퓨테이셔널하게 근사하는 방법.
네, 근사는 근사인데 그게 그러니까 뭐 어떤 좀 우리가 더티한 방법으로 혹은 휴리스틱한 방식의 어떤 근사적인 어떤 장치를 추가한다는 게 아니라 컴퓨터에서 그런 에러들, 그러니까 이게 컴퓨터가 100% 모든 값을 정확하게만 만든다면 사실 어떤 알고리즘을 써도 정확하게 같은 결과가 나올 텐데 컴퓨터가 이 알고리즘을 돌렸을 때 이게 불완전하게 돌기 때문에 이제 생길 수 있는 그런 거를 우리가 사전에 고려를 해갖고 우리 알고리즘을 더 똑똑한 알고리즘을 만드는 거예요. 근데 그 똑똑한 알고리즘 자체는 사실 컴퓨터가 완벽하다면 이 알고리즘이나 저 알고리즘이나 결과는 똑같아요. 네, 그러니까 뭐 그런 측면에서 좀 더 엘레강트한 뭔가를 좀 하는 거죠.
하려면은 A의 컬럼 벡터가 전부 다 일단 인디펜던트 해야 되고 A도 스퀘어해야 되고.
네, 그것도 좋은 지적인데 이제 A가 이제 리니얼리 인디펜던트 하지 않으면 그때가 어떤 경우냐면 여기서의 그 A 트랜스포즈 A 자체가 저게 이제 인버터블하지 않은 경우가 돼요. 그래서 이제 그때가 문제가 생기니까 그때를 그럼 어떻게 대입을 할 것이냐? 뭐 람다 I, 아까 감마 I 뭐 이거를 대입을 그걸 더해갖고 매트릭스가 그러면 하여튼 A가 하여튼 리니얼리 디펜던트한 컬럼을 가지면 A 트랜스포즈 A가 인버터블 하지 않아요. 저게 인버터블 하지 않고요. 그 두 개는 동치예요. 그러니까 다시 한번 말하면 그러니까 A는 스퀘어 매트릭스가 될 수가 있고 A는 렉탱귤러 매트릭스고 A 트랜스포즈 A는 무조건 스퀘어 매트릭스예요. 그렇죠? 그러니까 인버터빌리티는 A 트랜스포즈 A에서만 따질 수가 있고 왜냐면 스퀘어 매트릭스니까. 그 다음에 렉탱귤러 매트릭스 A에서는 우리가 이제 인버터블 하냐는 따질 수가 없고 다만 컬럼들이 리니얼리 인디펜던트 하냐를 따질 수가 있죠. 근데 이쪽에서 컬럼들이 리니얼리 인디펜던트 하다 그러면 그때는 A 트랜스포즈 A가 인버터블 하다. 거꾸로 A 트랜스포즈 A가 인버터블 하다 그러면 A는 리니얼리 인디펜던트 컬럼을 가져야 되고요. 이게 동치예요. 그러니까 왔다 갔다가 가능해요. 그리고 그 반대도 이렇게 가능하고. 그래서 이제 A가 리니얼리 디펜던트한 컬럼을 가지면 문제가 생기고 이거를 할 수가 없고 그래서 그때는 이제 A 자체에다가 우리가 하는 게 아니라 A 트랜스포즈 A를 구한 다음에 거기다가 이제 람다 I를 더해 감마 I를 더해주면 그러면 이제 그게 일단은 여기서는 이거 인버터블 해주니까. 네.
그러면은 이쯤에서 A가 인버터블 하지 않을 때 컬럼들이 디펜던트 한 게 있을 때 사용을 한다.
그렇긴 한데요. 이제 우리가 뭐 뒤쪽에서 또 그런 내용이 아마 나올 텐데 이게 매트릭스가 인버터블 하다 안 하다는 어떻게 보면 되게 흑백 논리잖아요. 인버터블 하면 한 거고 아니면 안 한 거고. 네. 그리고 그게 어떻게 보면은 그 뭘로 결정이 되냐면 그 디터미넌트라고 불리는 그 판별식이라고 불리는 이제 2차원, 2x2 매트릭스에서는 이제 AD-BC 있잖아요. 그게 우리가 매트릭스의 디터미넌트라고 부르고, 걔가 0이면 인버터블, 걔가 0이 아니면 인버터블, 걔가 0이면 인버터블이죠. 그죠? 근데 중요한 건 그 판별식이 예를 들면 0.000001이거나, 네. 그러니까 뭔가 이게 거의 이제 싱귤러가 될 뻔한 그런 매트릭스. 그러니까 인버터블은 한데 아주 뭔가 인버터블하지, 그러니까 거의 이제 난 인버터블한데 어떻게 겨우 인버터블해지? 뭐 그런 상황들을 고려를 해볼 수가 있어요. 그래서 이게 예를 들면 얼마나 인버터블하냐 그 정도를 우리가 그런 컨티뉴어스 밸류 측면에서 매핑을 혹은 생각을 할 수가 있고요. 그러니까 이게 뭐 아니면 도 인버터블 하냐 아니냐 이거 두 개만이 아니라. 그래서 그게 이제 뭐라고 부르냐면 그런 이제 컨디션 넘버라는 뭔가로 불려요. 그래서 컨디션 넘버가 0이면 그건 인버터블이고, 컨디션 넘버가 0.0001이다. 그러니까 뭐 대충 디터미넌트 같은 개념 생각해 보면 그거는 이게 거의 인버터블한 거예요. 아니 거의 난 인버터블한 거고. 근데 이제 중요한 건 그 수치가 이제 크면 그러니까 하여튼 그 컨디션 넘버는 그 반대 개념이긴 한데 어찌됐건 중요한 거는 얼마나 이게 인버터블 하냐에 대한 거를 이제 컨티뉴어스한 어떤 값으로 우리가 이 개념을 확장을 시켜볼 수가 있다는 거고.
함수로 나타낼 수 있는.
네, 있어요. 그게 이제 싱귤러 밸류 두 개의 이제 비율 같은 비율이거든요. 그래서 이제 그러니까 이제 제일 작은 그리고 제일 큰 싱귤러 밸류들의 두 개의 비율이 그게 이제 컨디션 넘버고, 그게 크면 클수록 이제 그 인버터블 하지 않은 게 되거든요. 약간 그런. 네. 근데
이게 되게 스트릭하게 인버터블한 행렬이어야지만 풀려야 되는 솔루션 같은 경우는 그 펑션 값의 스트레스를 크게 잡거나 그러니까 스트릭하게 잡아서 약간 하이퍼 파라미터처럼 아니면 그거의 펑션의 아웃풋을 어느 정도랄까 어느 수가 뭐몇 정도 이상이면 인버터블이라고 확실히 할 수 있다라고 할 수 있는 그런.
그게 이제 그거를 그냥 그런 하드 트레시홀드로 하진 않고요. 하드 트레시홀드로 하지 않고 그걸 어떻게 하냐면 그 매트릭스를 이제 컨디셔닝 한다 그러는데, 그러니까 그거를 컨디션 넘버를 더 좋게 만드는 식으로, 그러니까 우리가 올소고널 그러니까 어떻게 보면은 그러니까 얼마나 인버터블한 정도는 직관적으로는 뭐냐면 어떤 매트릭스가 가지고 있는 컬럼이 얼마나 리니얼리 인디펜던트하냐 디펜던트하냐예요. 그러니까 그것도 역시 마찬가지로 어떤 두 개의 벡터가 이렇게 있고 세 번째 벡터가 뭐 그냥 뭐 이렇게 생판 다른 디렉션을 포인팅하고 있다. 그러면 이거는 꽤 리니얼리 인디펜던트한 거고요. 그리고 맥시멀리 리니얼리 인디펜던트하다는 게 뭐냐? 이게 수직일 때가 맥시멀리 리니얼리 인디펜던트한 거예요. 어떻게 보면. 그리고 그럼 거꾸로 거의 리니얼 그러니까 굉장히 적게 리니얼리 인디펜던트하다는 거예요. 혹은 거의 리니얼리 디펜던트하다라는 건 뭐냐면 이 어떤 세 번째 벡터가 거의 이렇게 붙은 거죠. 혹은 그 각도 자체가 굉장히 작을 때 거의 리니얼리 디펜던트한 거잖아요. 그렇죠?
그거랑 상관없이 각도가 작아도 리니얼리가 90%지 완전 디펜던트하지 않으면 그 세 개의 벡터로 스페이스를 채울 수 있잖아요.
네, 그렇긴 해요. 그러니까 그게 그렇게 그러니까 조금이라도 각도가 0.0001도라도 벌어졌으면 그거는 사실 3디멘셔널 스페이스를 풀리 스팬하는데, 중요한 건 이제 우리의 지금 이 과목이 이제 Numerical Linear Algebra잖아요. 그 Numerical이라고 하는 뜻 자체가 뭐냐면 우리가 이제 finite number를 쓰는 컴퓨터를 쓰는 거기서 나타날 수 있는 이슈를 우리가 감안해서 우리가 그것까지 고려한 좀 더 아까도 뭐 비슷한 얘기를 했는데 좀 더 똑똑한 버전의 알고리즘을 만들어 둬야 된다라는 게 우리가 조금 이 Numerical Linear Algebra에서 다루는 토픽이거든요. 네, 그러니까 이게 무슨 말이냐면 이 아까도 뭐 이렇게 비슷한 예를 들었는데 여기서 이제 요걸 하면 이제 각도가 조금만 차이가 나면 그러니까 이게 약간 이런 게 있어요. 그러니까 이게 결국은 우리가 리니어 시스템을 푼다는 거는 뭐냐면 AX equal B를 푼다는 거는 A의 리니어 A가 두 개가 있어요. 그리고 X1, X2가 이렇게 있어요. 그러면 이게 주어진 벡터 B를 만족해야 되는 거예요. 이게 아까도 봤던 리스퀘어나 뭐 우리가 이제 피팅하고자 하는 뭐 머신러닝에서의 프로블럼들이 뭐 리그레션 같은 경우 뭐 대충 이런 식으로 많이 포뮬레이트가 돼요. 근데 이게 보면 이 두 개의 피처가 굉장히 방향이 비슷하다라고 하면 어떤 결과가 생기냐면 이렇게 돼 있고 이렇게 돼 있어요. 그러면 이제 이 예제 좀 들기가 좀 얘에 대해서 이제 이거의 솔루션이 나타내는 의미는 뭐냐면 이 주어진 벡터에 대해서 이 어떤 이게 B예요 지금 이게 A1, A2고 그러면 이거 두 개 뭔가 이 평행사 변형을 만들어서 얘는 대충 한 반 정도가 됐잖아요. 그러니까 이게 0.5고 이거는 한 1.1 정도가 됐으니까 이거 두 개가 우리의 솔루션이에요. 그리고 저 솔루션이 나타내는 건 뭐냐? 이게 이제 키고 몸무게예요. 그리고 얘는 이 사람이 살 뭔가 수명이에요. 그러니까 주어진 학습 데이터에 대해서 키와 몸무게를 가지고 우리가 수명을 예측하려고 할 때 거기에 붙는 코에피션트가 혹은 가중치가 결국 이 평행사 변형을 만드는 그 배율에 의해서 결정이 된다는 거죠. 그렇죠? 그러면 지금 이게 근데 이 각도가 조금이라도 틀어지거나 그러면 하여튼 이거는 지금 평행사 변형이 워낙 내로한 거기 때문에 예를 들면 이 점을 뭐 이런 거 하나를 만들려고 해보면 이게 어떻게 만들어야 되냐면 어떻게 만들어야 될까요? 이거 뒤로 가야 되나? 그렇죠. 뒤로 가야 되죠. 뒤로 이렇게 가고 얘가 그렇죠. 그리고 얘도 엄청 가서 이 두 개의 벡터가 엄청나게 가야만 꼭지점을 하나 만들 수가 있어요. 그렇죠? 그러니까 지금 보면 이게 다시 그려보면 여기 요 근처에 있는 요점 하나 나타내려고 지금 이런 걸 써야 되는 거예요. 그렇죠? 그러면 이때 코에피션트 값 자체가 굉장히 언스테이블 할 수가 있어요. 이 벡터가 아주 정확하지 않으면 저 배율 자체는 저 배율이 까딱 하면은 10이 어떤 정확한 값인데 까딱 잘못하면 이게 10,000 혹은 100만으로 우리 알고리즘을 구할 수가 있어요. 이게 곧 스테이블하지 않은 경우가 되거든요. 방향이 그래서 같은 방향이면 안 좋아요, 뭔가. 그래서 이제 우리 매트릭스가 리니얼리 디펜던트하다, 인디펜던트하다, 뭐 그것까지는 뭐 여기서 뭐 예를 들면 리스퀘어에서 뭐 이거 솔루션이 하여튼 리니얼리 인디펜던트만 하면 하여튼 저 솔루션은 있긴 한데 저거를 구할 때 우리가 이제 컴퓨터상에서 이제 넘버들을 나타낼 때 어떤 그 약간씩의 차이들이 에러들이 생기는데 뭐 3분의 1을 간단하게 못 나타내잖아요. 0.3333 이걸 못 나타내요 컴퓨터는. 그러니까 거기 그 살짝의 차이 때문에 우리 코에피션트도 그거에 따라서 작게 영향을 받으면 좋지만 영향을 너무 이렇게 크게 받을 수 있는 상황이 생긴다는 거예요. 그래서 이제 우리 매트릭스를 그래서 가능한 한 최대한 올소건을하게 그러니까 리니얼리 인디펜던트한 정도를 최대한 키우도록 즉 그 말은 우리한테 주어진 매트릭스 A의 컬럼들이 거의 올소고널 매트릭스 올소고널한 컬럼에 가깝도록 각도가 크게 가질 수 있도록 하면 그게 좋은 거거든요. 그래서 이거를 이렇게 풀지 않고 이거를 뭐 또 이렇게도 풀 수가 있어요. A를 우리가 QR 디컴포지션 했다 그러면 QRX equals B가 되잖아요. 그리고 Q 트랜스포즈 이렇게 해서 여기다가 이렇게 하면 결국은 X는 R 인버스의 Q 트랜스포즈 B라고 나타내질 수 있어요. 그러면 이렇게 푸는 방식이 있고요. 이렇게 푸는 방식이 있고 아까 이 X를 푸는 방식은 그냥 이 AX equal B에서 A 트랜스포즈 A 인버스 A 트랜스포즈 B 이렇게 푸는 방식이 있어요. 그러니까 두 가지 방식입니다. 하나는 A가 리니얼리 인디펜던트한데 중요한 건 그때 A를 거의 리니얼리 디펜던트한 컬럼을 가진 상황이면 뭔가 이게 아까 이런 거를 만들어내요. 근데 A를 뭔가 QR을 돌려서 그리고 그 QR도 좀 좋은 QR 알고리즘을 돌리면 QR을 돌릴 때도 저 Q를 좀 저런 에러에 대해서 조금 더 로버스트한 알고리즘을 우리가 만들 수가 있고, 그래서 그렇게 QR을 만들어서 이런 식으로, 그러니까 결국은 우리 솔루션, 이거랑 이거는 같은 솔루션이거든요. 그래서 저 위에 쪽을 쓰면 뭔가 아까 얘기했던 뭐 실제로 그 가중치 값이 10인데 그게 뭐 10,000, 100만 이런 식으로 나오는 거를 훨씬 더 방지를 해줘요. 그래서 이거를 이제 뭐 이게 큰 틀에서는 이걸 뭐라고 부르냐면 이제 그런 컨디션 넘버를 좋게 한다라고 이야기를 해요. 그러니까 결국은 이 R은, 그러니까 이게 어떻게 보면 RX 이퀄 Q 트랜스포즈 B, 이게 어떤 새로운 형태의 AX 이퀄 B 형태가 된 거잖아요. 그러면 이 R은 기본적으로 쟤는 기본적으로 어퍼 트라이앵글러 매트릭스예요. QR 디컴포지션스. 그러면 그 일단 다이아고널 혹은 그런 어퍼 트라이앵글러 매트릭스 이런 것들은 컨디션 넘버가 되게 좋아요. 그러니까 생각을 해보면 첫 번째 벡터는 쉬는 시간이 많이 지났네. 이 첫 번째 벡터는 지금 되게 중요한 얘기들을 하고 있는데, 이 첫 번째 벡터는 x축으로만 있죠. 두 번째 혹은 그 이후의 축으로는 모두 다 0인 값을 가지잖아요. 근데 두 번째 벡터는 첫 번째, 두 번째 디멘전이 난제로인 거잖아요. 그러니까 첫 번째 벡터와의 일단은 각도 자체가 꽤 큰 각도를 준단 말이에요. 그렇기 때문에 저 어퍼 트라이앵글러 매트릭스나 다이아고널 매트릭스는 기본적으로 컨디션 넘버 같은 게 굉장히 좋아요. 혹은 리니얼리 인디펜던트한 그 정도 자체가 충분히 리니얼리 인디펜던트해요. 뭐 거의 요런 각도 이런 거 잘 없단 말이죠. 그렇기 때문에 저렇게 RX equals Q 트랜스포즈 B로 만들면 훨씬 더 좋은, 그러니까 로버스트하게, 그러니까 내부적으로 계산상에서 컴퓨터가 발생할 수 있는 에러가 있다 하더라도 훨씬 더 좋은 거예요. 그래서 이제 어떤 이 리니어, 요즘은 그런 거를 많이는 안 쓰는 것 같은데, 일단 이 리니어 시스템이 AX equals B라고 하는 이 결국 이 리스트 스퀘어 요거 풀려고 사람들이 엄청나게 여러 가지 노력들을 많이 하고 있는데, 이 A를 지금 이런 식으로 QRA에서 컨디션 넘버를 좋게 하는 방식도 있고, 이거 말고 되게 다양하게 그 컨디션 넘버를 좋게 하는 방식들이 있고, 그런 걸 이제 뭐라고 부르냐면 이제 프리 컨디셔닝이라고 불러요. 이런 프리 컨디셔닝에 기반하는 기법들이 무슨 그런 컨주게이트 그레디언트에 기반한 뭐 어떤 리니어 시스템 솔버, 혹은 뭐 이것저것 뭐 있거든요. 나도 잘 몰라요. 근데 하여튼 중요한 건 프리 컨디셔닝이라는 말 자체는 뭐냐면 이런 이제 아까 얘기했던 그 컴퓨터에서 발생할 수 있는 그 에러 같은 것들을 좀 줄이기 위해서, 혹은 그게 결국은 뭐냐, 우리가 풀어야 되는 AX equal B에서 A의 컬럼들을 최대한 좀 올소거널하게 만들어주고 싶다는 거예요. 그러니까 어떻게 보면은 QR 디컴포지션을 한다는 거는 우리가 컨디션 넘버를 맥시멀리 좋게 만들어주고 싶다는 거고, 그렇게까지는 좀 못하더라도, 왜냐면 저 QR도 하려고 하면 또 해야 되는 게 많으니까 그렇게 하지는 않더라도 적절한 방식으로 그 컨디션 넘버를 조금씩 개선할 수 있는 그런 이터러티브한 방식들이 좀 있어요. 그래서 이제 그런 것들이 이제 그 어떤 또 이런 리니어 시스템, 하여튼 뭐 이 AX equal B 저거 하나 풀려고 하여튼 엄청나게 많은 이론과 내용과 뭐 이런 것들이 많이 있거든요. 뭐 크라일롭 서브스페이스니 뭐 거기서 나타나는 뭐 그런 거, 아놀디 어쩌고니 뭐 혹은 뭐 AR 팩, 린 팩 뭐 이런 거 들어가는지 모르겠는데, 그런 것들이 이제 실제로 그런 아마도 뭐 그 쿠다나 뭐 그런 GPU 상에서도 그런 이제 리니어 알지브라 라이브러리로서 이제 제공이 되는 것들이 뭐 우리가 알고 있는 뭐 QR, LU 뭐 이런 거 말고 이제 뭐 저런 뭐 아놀디 어쩌고 뭐 컨주게이트 그레디언트, CG 뭐 이런 것들이 일단은 저런 뭔가 컨디션 넘버를 좋은 형태로 만드는 식으로 일단 뭔가 바꿔서 좀 리니어 시스템 푸는. Okay, so okay, so we discussed about this projection, right? So projection is represented in this form, right? And then, yeah, last time we discussed about this idempotent thing, right? So idempotent means yeah, P transpose equals P, and yeah, intuitively, I mean, if we imagine like intuitive process of this orthogonal projection, then we orthogonally project one point onto the column space of an A, and then if we project that already projected point once again, and then we will obtain the exact same point, right? And so, if P represents the orthogonal projection, and then PU should be, and then another P will result in the same projection point of PU, right? And thus, this guy, P squared equals U, and P squared times U and PU. Okay, so this is a, I mean, this should be satisfied for any given U, right? Any given U, right? And so, the only way to satisfy this for any given U is this guy, P transpose P, right? And so our orthogonal projection is a one representative example of idempotent matrix thing. Okay, and yeah, let's verify that. Okay, so yeah, again, this guy. What is P given the matrix A? Okay, so we want to project it orthogonally to column space of an A, and then A times A transpose A inverse and A transpose, right? So that, oops. Sorry, so here, yeah, right, okay. So A is this red part, right? Not this pink one. A, this whole part. So that is our P, right? So this was our P, and let's verify if it is P squared. And we will multiply it once again. Okay, and then A and A transpose A inverse and this part. A transpose A, then let's just put the parentheses because we can just yeah, multiply the latter ones first. Okay, and you will see this guy is cancelled once, right? And thus it is A and A transpose A inverse A transpose. Okay, so this is our original matrix P. So yeah, we can easily prove that P squared is P. And also, in case we are given the matrix Q, which has orthonormal columns, and this P is, I mean, because this part is identity, right? And so P will be Q transpose, right? And then Q transpose Q transpose is our P squared, and yeah, Q transpose Q is identity, right? And thus Q transpose is our result, which is the same as just P. Okay, and here so let me ask a question. Is it possible that P is is it possible that A is a rectangular matrix, or should A be square matrix all the time? So here, yeah, in this example, A is already a rectangular matrix, right? Because in three-dimensional space, A has two columns, right? So A has the size of 3 by 2, right? So A is, of course, yeah, A can be like rectangular matrix, right? Okay, and similarly, this Q can be rectangular matrix, right? Q just have the also normal columns, but not necessarily a square matrix, right? So for example, A was like 3 by 2 matrix. And then what is our QR? So we have, so this is an A, this is Q, and our R is this, and then non-zero entries are, the R is an upper triangular matrix, right? So this is the representation of QR decomposition, right? So my point is that Q can be rectangular matrix, of course, right? And then in that case, so let me point out this first. So this Q is currently 3 by 2, but is it possible that this Q is Q has a more number of rows, more number of columns than rows? So for example, is it possible that Q has this form, 2 by 3? Is it possible or not? So again, the requirement of the matrix Q is that we have to have also normal columns. Also normal columns. So is it possible that?
No.
Why?
Because we cannot have more than 2 independent, linearly independent.
Right. That's right. Yeah. So in this case, we have, so these 3 vectors are living in 2-dimensional space, right? So in the 2-dimensional space, we can extract out 2 linearly independent or 2 also orthogonal or also normal columns at most in 2-dimensional space, right? So in this case, we are already given 3 vectors in smaller space of 2-dimensional space, and thus we cannot have the also normal columns in this form. Okay. So again, the number of rows should be equal to or greater than the number of columns in order to be a also normal. The matrix that has also normal columns. So again, let's clarify the terms. So also normal columns means in our matrix, every column, every pair of columns is also normal with each other, and not, between the orthogonal and also normal, the also normal has additional condition that the vector length is all 1, right? So that is the definition of being also normal, and also our matrix can have also normal columns for this rectangular matrix. But in this rectangular matrix, again, we need to have more number of rows than the number of columns, or they should be equal, right? So there are these 2 possible cases. And but in the case of a square matrix, okay, in particular, as a special case, if our matrix is a square matrix, and that square matrix that has the also normal columns, and that matrix is called orthogonal matrix. Okay, so orthogonal matrix is the same as the square matrix. Again, square matrix that has also normal columns. Okay, so that's the definition of this orthogonal matrix. Okay, so back to this. So here, so let me ask another question: Is Q invertible or not? So this question doesn't make sense at all, because Q is a rectangular matrix, right? So rectangular matrix, but still Q transpose Q is identity, right? Because we have a Q here, and so if we multiply Q transpose on the left, right. So in this case, we have the 2 also normal columns, and also they are Yeah, they are multiplied as rows on the left, and thus it will produce identity matrix. So you can easily see the proof, right? So once you just apply the inner product rule. Okay, so we can easily verify that if your matrix has also normal columns, and then this guy is always true, right? But what about Q transpose? This cannot be an identity matrix, right? Okay, so in this case of an QQ transpose, although it is not an identity matrix, but this guy is actually our P, right? So what's the meaning of P? P is orthogonal projection of any given vector onto the column space of these two orthonormal vectors, right? So yeah, in the case of a rectangular matrix, and Q transpose Q, rectangular matrix that has also normal columns, Q transpose Q becomes identity, and QQ transpose works as the orthogonal projection matrix. Okay, and also let's also think of square matrix. For example, having 3 columns and 3 rows, and in this case, not only this guy being true, but also this guy is also identity matrix, right? In the case of square matrix, right? Again, the square matrix, if we found one kind of matrix of this in the place of this QT that makes this something times original matrix equals identity, and then if we reverse the order, and that should also produce identity matrix in the case of square matrix. And also its meaning, it will be still a projection, right? Projection. So our projection in the case of square matrix, square orthogonal matrix, and our projection will be identity matrix. And so what does that mean? So we perform orthogonal projection, but that projection is identity, which doesn't change the input vector at all. So what does that mean? So when do we have the identity mapping for our orthogonal projection?
It's already in the space.
Yeah, right. That's right. Yeah. So if one point is already, given point is already within the column space of the matrix, and then the projection will not change at all, right? Okay. So in this case, we can think of a little bit less intuitive, but easy to understand the aspect that, So in the case of three-dimensional space, for example, suppose we found three orthonormal vectors, and we form orthogonal matrix that has these 3 columns, right? And then once we project any given point in the three-dimensional space, and then projecting it onto the subspace spanned by these 3 vectors will remain the same point, right? And that means our subspace spanned by these 3 vectors is already the entire space. So here, once we project one point onto the entire space, and then it will not change that point at all, right? And this characteristic will also hold true even when we don't have the orthogonal column. So in other words, if A is a 3x3 matrix, A is a 3x3 matrix, and A has a 3 linearly independent columns, that spans our entire three-dimensional space, and then our projection onto the column space of an A will be just the same point, right? So how can we verify that? By just checking, by looking at the formula that we obtained over here. So this guy, or let's look at this guy. So again, the situation is, for example, A is 3 by 3 matrix that is linearly that has the linearly independent column. So again, A is 3 by 3, which is a square matrix, right? And then A has 3 linearly independent columns. And what does that mean? So in the case of square matrix, having linearly independent column is equivalent to invariable, right? So A is invariable when A is a square and A has linearly independent columns. And also, if you're given a square matrix and your columns are linearly independent, and then your matrix is invariable, right? Okay, so we got this one, and here if A is an invariable matrix, okay, and then what is the inverse matrix of this guy? We can actually decompose it into this form. So you guys know AB inverse is A B inverse and A inverse, right? Here we need additional assumption that A and B are invariable matrix, which means A and B are square matrix. So in the previous case, so let's look at this form, the form of this A transpose A. A transpose A is something like this. So 2 by 3, 3 by 2. So that way we were able to produce at least the square matrix, and then if it is an invariable, and then we can apply the inverse matrix, right? But this matrix A transpose and A is not even a square matrix, so we cannot apply the inverse operator onto each of these two matrices, right? So usually we cannot represent, or we cannot use this equation here, right? But in the case of in the special case of A being 3 by 3 invariable matrix, okay, so in this case it can be represented as this form, and thus A times, so we basically switch the order and then apply the inverse operator. So A inverse and A transpose inverse times A transpose, right? So this guy is cancelled out, and this guy is also cancelled out, and thus it will give us the identity matrix. And thus our projection matrix will also be identity. Any questions so far?
I don't understand why, if you apply the Gaussian process, you guarantee that the point. I understand that you guarantee that the point comes in the same space. How do you guarantee it gets in the same position in the space?
So I was talking about the special case where Q is orthogonal matrix. So in general, Q can have So in the case of A being like this 3 by 2 matrix, and then the corresponding Q will also be 3 by 2. Okay, so in this case, even though Q transpose Q is identity, but Q transpose is not identity, right? And instead, this guy will work as our orthogonal projection kind of operator or transformation matrix, right? But in the special case where Q is an orthogonal matrix, which is a square matrix, okay? Square matrix having 3 columns in a 3-dimensional space. In this case, not only this is true, but also this is also true, right? And thus QQ transpose is identity. And what does that mean? Our projection should produce the identity mapping, right? And that is because we have a three also normal columns provided in our matrix P or Q. And then if we consider the span of these three-dimensional three vectors living in the three-dimensional space, and then that will produce the entire three-dimensional space. So the subspace or column space of this matrix will be just R3, which is our entire space, right? And so projecting it onto the entire space will remain the make the point stay the same, right? So that way we can understand why this guy should be identity matrix. Okay. So again, we were talking about the special case where Q is square and having also normal columns. Does it make sense?
Yeah, I meant in the case of the rectangular matrix, just why if you project on A or on the
Q
or Q, why the points end up in the same place. I understand why they end up in the same space, but not necessarily the exact same place.
So, in the case of this this 3x2 matrix that has just also normal columns, in this case, when projecting it onto the column space of this matrix, it will not be the same point.
Then, if you go back to the original these squares, then do you have to sort of rotate it back for it to make sense?
Okay, so we consider the non-also normal column case where we are given A, and then you are considering we just did the Gram-Schmidt process to obtain Q corresponding to given input A. Is it correct?
Yeah.
Okay, and then what?
Let's say you plug in Q instead of A. You sort of have to rotate it back. Or
I see. So you mean why is this result the same as when plugging Q into this A, right? So that is your question?
Yeah.
Right. So intuitively it makes sense, right? Because the space, column space should be the same, right? So basically so I haven't proved it in detail, but let's try. So we are given A, and then we consider the orthogonal projection onto column space of an A, given the vector U, and then it is just A transpose A inverse A transpose and B. Yeah, so this is the orthogonal projector. And now let's think of A being QR, right? Where column space of an A is column space of Q, right? So in this situation, will this be the same as Q and Q transpose Q inverse Q transpose and B, and this will be gone because of the fact that Q transpose Q will be identity. And so again, will this guy be Q transpose B? Right? So we have to prove that. So that is your question, right? Is it correct? Right? Is it your question or not?
Yeah, I just understand that it spans the same space.
Right.
But I don't necessarily see why this works.
Oh, okay. Okay. So again, intuitively we kind kind of have an understanding or intuition that so given the same plane, we can have a different versions or different sets of a basis vectors, right? Given the same plane, we can use, so let's just imagine this kind of plane. We can use these two vectors as our basis, or this vector, and so on, right? And so regardless of any particular set of bases, as long as their span is still remaining the same, and then the orthogonal projection, projected point should stay the same, right? So that is kind of intuitive understanding, but we haven't proved it, right, in more detail. So did anyone prove it? I'm not sure if I can prove it. So let's just plug this in, QR, and R transpose Q R inverse. Oops, this should be U. So it is gone. Okay, yeah, I think it is approved. Okay, so Q transpose Q is gone, right? Because that is identity, right? And now QR and R transpose R inverse and R transpose Q transpose, right? Okay, here let's just let's focus on R. So what is R? In the QR decomposition, so this is our QR, right? So even if A has, so here, we need an additional assumption, which is let's assume that A has also normal columns. A is a linearly independent column. Okay? Again, A is not having also normal columns, but A at least has also linearly independent columns, and thus A transpose A will be invariable. And also, in this particular case, our QR decomposition, the shape will be exactly like this matrix shape. But here, the point is, what about R? Is R invariable or not? So if we have two columns, okay, and let's briefly discuss about the interpretation of this QR decomposition. So once we obtain this QR decomposition through the Gram-Schmidt process, and then it can be understood as this. So we have the first column in A, and we want to reconstruct that first column as a linear combination of these two columns by using the linear combination coefficient of these two, right? Because that is the column combination perspective, right? But here we don't use the second column because we have 0 here, right? And then this guy is multiplied with this and this. So in the first step, this is just nothing but the normalization of this first column into unit vector, and then scalar multiple to just recover or reconstruct the original column, right? What about the second one? Okay. The second one, we have this second one over here, and this guy is the linear combination of the same two of the same vectors, right? But here, those two are the vectors that we constructed through our Gram-Schmidt process, right? And then we have a normalized version of the first vector, and this vector is the unit vector or orthogonalized basis vector from the second guy, right? So let's get back to this. Okay, let me give an example. So suppose A has the first column as 1, 1, 1, and the second column as 1, 0, 0. So let's do the Gram-Schmidt process. And then what is the Q? What is the Q? Q is right, and we don't know yet the second column, but we have no problem of constructing the first column corresponding to this green part as the linear combination of these two, and that linear combination will be this, right? So this is how we build this matrix decomposition through our Gram-Schmidt process. Okay, and then now we project this guy onto this previously constructed orthonormal basis, right? And then let's see. So we need these two, and also this part, right? And then what about this part? So we need to reconstruct the second given vector as a linear combination of these two, and what will be the linear combination coefficient that is multiplied with the second one. So in this case, pictorially, in this figure, so we want to represent A as a linear combination of U and the new also normal vector that's reconstructed, right? So what is this guy? This guy will be U times what? U times this guy, A times U, A inner product with U, right? So that inner product was what? Inner product is 1, right? Inner product is 1. So this value should be 1, right? So again, we reconstruct this second column as a linear combination of these two. Then this guy times the projected length, right? This is our length, right? And that length came from the inner product between this guy and this guy. 네, 괜찮아요. 끄기가 어려웠나 봐요. 요즘은 대충 아무 버튼이나 다 눌러도 꺼지지 않나요? 궁금해서. 저런 것도 저거 폰을 만든 사람의 어떤 고객을 배려하는 이런 게 다. 네, 이게 잘못 계산했죠? 여기, 네, 아까 저기 이너 프로덕트가 스퀘어 루트 1 오버 스퀘어 루트 3였죠? Okay, so and then we obtain the remaining component like this guy, right? This guy, and then we further normalize it, right, into the unit length vector, and that unit length vector, let's see, was this guy, 2 over square root 6 and negative 1 divided by square root of 6, right? And so that is like and this guy is finally represented as the scaling factor, right? Scaling factor of this blue orthogonal part into unit length vector, right? So this is how we construct this QR decomposition in this matrix decomposition form from the Gram-Schmidt process, right? Okay, so if second column, or while doing the Gram-Schmidt process, so first, second, and the third, and so on. I mean, the first column, second column, and so on. So once, so suppose we are at the maybe fifth column, and if this fifth column is linearly independent of the previous 4 columns, and then that blue part, okay, blue part is what? We subtract the original vector of the fifth column, from that fifth column, we subtract the projection of that fifth column onto all the previous 4 columns, right? And then the remaining vector will be like this, really orthogonal vector, like this blue part, right? So if that blue part is non-zero vector, so again, if that blue part is non-zero vector, and then we will be able to normalize it so that it can have a unit length, right? And then we can fill out the fifth column of our fifth normal, also normal vector, and also in the corresponding columns at the diagonal element. Diagonal element for this guy, and so on. These will be just a normalization factor. So as long as we have non-zero vectors after subtracting the orthogonal projection from the original vector, and then all the diagonal elements will be non-zero, right? But let's think of like a linearly dependent case where, so even in the simple case, we can also think about it. So the first vector and the second vector, suppose that is a linearly dependent of the first vector, and then that vector will be along the line, right? And then once we do the orthogonal projection, and then it will be the same point as the second vector, and then once we subtract it, and this blue part will be completely zero vector, right? And then there is no way to normalize it, right? So in that case, we have to, we cannot construct our orthonormal basis vector from that linearly dependent vector, and then we have to move on actually to the next column to see if that gives us a new orthonormal vector. So like, at a high level, so you can think of this Gram-Schmitt's process and the reconstruction of this A equals QR in this form. So even though QR decomposition is defined for the linearly independent, the matrix that has a linearly independent vectors, but we can, we have no problem of continuing our Gram-Schmitt's process for the linearly, the matrix that has a linearly dependent column. So for example, so in this 3x4 cases, we can definitely say that this matrix will have a linearly dependent vectors, right? Because we have 4 vectors in 3-dimensional space. And let's indicate whether each column vector is linearly independent or dependent in this one. So I, D, D, I. So it is indicating when each column vectors, when adding each column vector one by one, and whether that vector is represented as a linear combination of the previous vectors. So we explained this process, right? When discussing Gaussian elimination and the pivot and things like that, right? Okay, so in this case, so again, the point is, intent of the Gram-Schmitt's process is to construct the orthonormal basis of the given subspace. So this is our given subspace spanned by the 4 different columns, whether some of them are linearly independent or not. Okay, so we have a matrix A and Q. So basically, we want to equate these 2 subspace, right? And so we want to find out the orthonormal columns, and then okay. So I already drew this Q as 3x2, which has 2 linearly, 2 orthonormal columns. So why do we have them as 2? Why do we have 2 orthonormal columns? Because we have only 2 linearly independent in our A, right? But let's think of the Gram-Schmidt process anyways, given this matrix. And then so given this matrix, we will first normalize it to produce the first orthonormal vector. And so this is Q, and this is R, right? So we can fill out the first column of an R. So this is a kind of some normalization factor and all 0, right? So this is how we populate Q and R column-wise, right? So far so good? Okay, and then let's think of the Gram-Schmidt process of the second vector. So in this case, because this guy is linearly dependent, so once we project it onto the subspace spanned by the previous vectors, and then after subtracting that projection from this vector, and then the remaining vector will be completely 0, right? Completely 0. So we can skip that part, right? So that means, we cannot construct or we cannot add any non-zero or linearly or any orthonormal basis vectors to Q, right? But still, how about R? Can we construct R? So still, we want to obtain A being equal to QR. So in order to reconstruct the second column, and then what will be the corresponding second column in R? So in that case, we will have some non-zero, right? Because we can still have the component explained by the first component. And what about the remaining ones? So it will be all 0. Because the second one can be fully represented by only using the previous columns, right? So this guy will work as a linear combination coefficient for these, right? So we don't care about the later or latter columns because we can just set it as 0, right? Okay, so this is a okay. And then let's move to the third column. So in that case, it will still produce no non-zero or no orthonormal basis columns. And what about the R? R will be also like this, right? And then finally we have another linearly independent one. And then now we can fill out the second column in our Q, right? And then what about the pattern of an R? So here the star is like non-zero values. So some value and 0, right? And that's it, right? So we reach at the end of our last column in our matrix A, right? And that's when we just finish. That's when we complete our the construction of Q, and thus we don't need this part at all. So correspondingly, Q will have 2 columns, right? And thus R will have 2 rows, right? That corresponds to the linear combination coefficient. So this is like this is a staircase shape that is similar to the result of the Gaussian elimination that reveals where the pivot is, right? Okay, so back to the case where A has linearly independent columns. Okay, A has linearly independent columns, and then for every A, so it will all be I or independent columns. So for each column, we should be able to construct or add their own basis vector, also normal basis vectors, right? And then what about this star kind of thing? So star, yeah, those star values, which is the lowermost part, I mean those two elements that is corresponding to the normalization factor when we finally obtained non-zero remaining part after subtracting the orthogonal projection, right? And then these are just nothing but the normalization factor. And once we obtain non-zero vector, and then we will obtain non-zero element on this on these lowermost things. Okay, and so suppose we have like 3 linearly independent columns. We don't even know the number of rows in this case. Okay, so in this case, so what about Q? So Q will be still, yeah, another version of the 3-dimensional vector, right? But yeah, I want to discuss about the pattern of R. So pattern of R will be something like this, and here those values are guaranteed to be non-zero, right? So does it make sense? So because we obtained non-zero remaining vector, right, after subtracting orthogonal projection from the previous vectors, okay, and then these are just a normalizing factor. So we have non-zero vector, and thus normalization factor will also be non-zero. Okay, and here, so we can guarantee, we obtain this upper triangular matrix that guarantees to have non-zero values along the diagonal elements. So what can we guarantee that, or what can also draw? What kind of conclusion that we can draw? And in this case, yeah, non-zero element along the diagonal for the upper triangular matrix, and then it will be invertible matrix, right? So why is a upper triangular matrix is an invertible matrix? So yeah, we can also intuitively think about it. So so yeah, suppose we are given this particular matrix, and then let's check whether each columns are linearly independent from the previous vectors. So the first vector and the second vector, so we have 0 here, right? And so in order to explain this part, I mean, we have no way to explain this vector that has non-zero elements in the second dimension by using all the vectors that has 0 in the corresponding dimension, right? And so this should be linearly independent from the previous one, and this guy also has the same property. So, and also from the another kind of a mechanical kind of perspective. So what is the, I mean, how can we determine whether the matrix is invertible or not? So we basically compute this determinant of an A, right? Like AD minus BC kind of thing, right? So if it is non-zero, and then it is invertible, and if it is 0, and then it is non-invertible. And first of all, this determinant is only defined for the square matrix. And why? I mean, determinant is only defined for the square matrix, and that's why we can use this determinant as a deciding factor for being invertibility, for the invertibility, okay? So again, determinant is defined for the square matrix. Okay, and then, what is the determinant of this upper triangular matrix? So does anyone know the formula? 네. So the formula is the product of all the diagonal elements. Okay, so if they are all non-zero, then it will be non-zero, and thus it will be invertible. And what about this case? Like this case. So, so in that case, we can also understand the invertibility from the perspective of this determinant of upper triangular matrix. So in this case, if one column has non-zero, if one column has 0 and 3 along this diagonal element, okay, and then it will be like a shift, right? But still, determinant will just look at the diagonal element, but at some point, if we found the 0, and then the determinant will be 0. But anyways, this guy, I mean, in this particular matrix, it may or may not be square matrix, so the determinant may not make sense, but yeah, if we just only consider the square matrix, and then you can think of that pattern of the patterns, pivot position patterns, and then okay, so here, my point is, if A is a linearly independent column, and R, this matrix R is square matrix, and upper triangular matrix, and diagonal elements will all be non-zero, right? So here I didn't even specify the number of dimension in our Q, I mean the number of rows, so it can be maybe 5, okay? And then if it is a linearly dependent, then we are guaranteed to produce 3 columns, right? 3 also normal columns, and then this guy will, can be represented as, for each column we need a linear combination coefficient by using these 3 columns, right? So we need a 3 coefficient, and for the second one we need another set of linear combination coefficient and another set, right? And so the number of vectors that we have to represent is the same as the number of vectors that we use as our linear combination basis, right? And thus this R is always the square matrix, and also if they are linearly independent, then that non-zero element will all be placed in the diagonal element, and thus R is invariable. Okay. So I wanted to say that R is invariable. Okay, so back to here. So R is square matrix and invariable, right? And so R transpose R of the inverse, inverse of this R transpose R can be actually get out of this parentheses, right? Because each individual R and R transpose is invariable. Okay, and then QR, and this part is R inverse and R transpose inverse, R transpose Q transpose, and thus this will be cancelled out, and then we obtained Q transpose Q, right, from here. So we also we were able to prove this thing as well. Any questions so far? So let's quickly wrap up this chapter. So you guys you guys know the norm or metric. So norm or metric is the intuitive meaning is the vector length. Okay, vector length. So given m-dimensional vector, it is the function of mapping it into a scalar, which is representing the vector length, right? And these 3 conditions are satisfied, and then this function that gives us some notion of a vector length is called norm or a metric. And here, one interesting property is the second one. So the second one is called what? Second one is called, yeah, it is called the triangular inequality. So vector x, vector y, and this guy is x plus y, right? And so the vector length of this guy is always smaller than or equal to the sum of individual vector length sum. And in case of the 2 norm, yeah, it has this property of the inner product. And this is a generalization of 2 norm, and it's called the P norm, right? P norm. So P is usually, yeah, integer, and yeah, it can be non-integer, but in general, this P is greater than or equal to 1. So what if P is smaller than 1? So in that case, it is not a metric. So among these, so one of the important properties is not holding true, and that is this triangular inequality, right? And what about this? P being equal to 1. In the case of P being 1, then that is actually at the borderline, which means this triangular inequality is actually becoming an equality. So yeah, let's verify that, like 3, 1, 2, 4. Yeah. Okay, so in this case, how do we compute the 1 norm? In this case, L1 norm is a 5, 5. Okay, let's just change it as 5, and then it will be 9. And then the norm of 1 norm will be 5 plus 9, which is 14, right? And then this guy is the norm of having 8 and 6, and so it's 14, right? So in this case, 1 norm will be satisfying this triangular inequality. But I just found that if the sign is different, and then it's not equal, right? So it becomes strictly inequality, right? But that is kind of trivial case, but yeah. Okay, and then also in the case of an other norm where P is 2 or 3 and so on, when do we achieve this equality in our triangular inequality? So what's the condition about it? So if x and y is a scalar multiple, or parallel. So if this holds true, and then triangular inequality becomes equality, right? And also, let me make one last comment. So we usually use the P being larger than or equal to 1, but if it is less than 1, and then it breaks, or it makes this, it doesn't make this triangular inequality true, right? And so, in the case of our regularization, we typically use L1 or L2 regularization and things like that, but sometimes we actually use L0 norm regularization and also L infinity norm regularization. So what's the L infinity regularization? So it's like 3 to the power of infinity and 5 to the power of an infinity and 1 over infinity, right? And so it is what? Max value. It picks up the max value of 5 because, And what about L0 norm? It's used as a kind of a sparsity kind of a regularizer, So yeah, so the 1, 1, 2 in this case, something like this. But yeah, it's not very intuitive. But yeah, so we know that this guy is a 1 and 1, right? So yeah, so if we just set it as 1, and then it would be 2, right? But what if we have a 1 and 0, and then 0 to the power of 0, it is not even defined as I know. I'm not sure, but 0 to the power of 0 can be considered as 0, right? And so in that case, yeah, it is actually counting the non-zero element. So if we add this L0 norm regularizer and then minimize it, and then we don't actually care about the actual magnitude of our parameters learned, right? But we actually care about non-zero parameters. Okay, so that's it for today. And again, we will have a maker lecture this Friday at 2. Yeah, we will have no quiz this Friday.
그것도
시험에요. 이거를 금요일에 나가. 내가 그날 그 강의 비디오를 바로 올려줄게.
토요일 날까지 하는 걸로 이제 시험
네, 아마 그럴 것 같습니다.